You know, it's kind of cool to think about electrical circuits as their own language. I mean, it's the language that literally powers our entire world, right? And just like any language, it has its own rules, its own grammar. Well, today we're going to learn the most important grammatical rule of them all. It's the one that unlocks our ability to read any circuit correctly, the passive sign convention. So to really get why this rule is so important, we have to start with a bit of a mystery. It's a riddle that trips up almost everyone when they're starting out in electronics, and at first glance, it really looks like it breaks the laws of physics.
So here's the puzzle. You've got a simple resistor, a component whose only job is to consume power, right? It just gets warm. But when we hook up our voltmeter, it reads negative 100 volts. Now, a negative voltage, that usually means you're looking at a power source, like a battery. So what on earth is going on here? Is this little resistor somehow generating power? The answer, of course, is no. And the key to understanding why is all in that grammar of circuits.
To solve this, first, let's do a super quick review of our three main characters: voltage, current, and power.
First up is voltage. Just think of it as electrical pressure or potential. The absolutely crucial thing to remember is that voltage isn't a cross variable. It's always a measurement of the difference between two different points.
Then you've got current. This is the actual flow, the movement of charge. And unlike voltage, current is a through variable. We're measuring how much stuff is flowing past a single point in the wire.
And finally, there's power. Power is simply the rate that energy is being transferred, and you calculate it by multiplying voltage times current. The sign of that power, whether it's positive or negative, is what tells us if something is consuming energy or supplying it. And that sign, well, that's the very heart of our resistor riddle.
Okay, so here is the most important idea of this whole explainer. A circuit diagram is just a map. It's not the actual territory. The symbols we draw are just assumptions we make before we start doing the math. This is such a key distinction to make. The plus signs, the minus signs, the arrows showing current, that's all just our map. It's our best guess to start with. The physical territory, which way the current actually flows and where the higher voltage really is, that's all determined by physics. Our math, as long as we follow the rules, will tell us if our map was right or wrong.
This quote from a university lecture just nails it. Seeing a negative reading on your meter doesn't mean physics has suddenly taken a day off. It just means your tool is hooked up backwards compared to the labels you drew on your diagram. That negative sign isn't a mistake, it's information.
So how do we use this information and not get confused? How do we make sure our map always leads us to the right answer? Well, we use a simple, universal rule. It's called the passive sign convention, or PSC for short. You can think of it as an agreement, a rule of grammar that engineers all over the world use. It lets us interpret the signs in our math correctly every single time.
And here's exactly how it works. Look at the image on the left. The current arrow goes into the positive terminal. That follows the convention. Now look at the right. The current arrow goes into the negative terminal. That clashes with the convention. That's it. That's the whole rule in a single picture. So here it is in one sentence. If we draw our diagram so the current arrow goes into the positive voltage terminal, we assume the component is passive, that it's absorbing power. Then, when we calculate power using P equals V times I, a positive result confirms it's absorbing energy, and a negative result tells us it's actually supplying it.
All right, we've got the rule. Let's go back and use it to finally crack the code and solve that resistor riddle.
Okay, let's walk through this. Step 1. We look at our diagram. The current arrow is entering the negative terminal. That's a clash with our convention. Step 2, because it clashes, we can't just use P equals V times I. We have to introduce a negative sign to correct for our clashing labels. So our formula is now P equals negative V times I. Step 3, we plug in the numbers. Power equals negative times our measured negative 100 volts times 0.1 amps. And what happens? The two negatives cancel out, giving us a result of positive 10 watts. And there you have it, riddle solved. The positive sign for power confirms that the resistor is doing exactly what it's supposed to do, absorbing energy.
And this right here is the big takeaway. When you follow the passive sign convention, the math will always tell you the truth. If you calculate power and get a negative number, you know that component is actively supplying energy, like a battery. If you get a positive number, it's passively consuming energy, like our resistor or a light bulb.
So why does this one little rule matter so much? I mean, what's the big deal? Well, it's not just about getting one component right. It's about making sure our understanding of the entire circuit is consistent and correct.
It all comes down to one of the most fundamental laws in the entire universe. the conservation of energy. In any closed circuit, you can't create or destroy power. For every watt of power that gets absorbed, a watt has to be supplied from somewhere. The passive sign convention is basically the accounting system that makes sure this law is always balanced in our calculations. The sum of all the power in any circuit has to be zero.
You know, the need to clearly define these ideas has been with us since the very beginning. More than 200 years ago, André-Marie Ampère, one of the great pioneers of this field, was already setting up the basic vocabulary for what he called electric tension and electric current. Our sign convention is just the modern grammar for that amazing language he helped create.
So, if the passive sign convention is the grammar of circuits, then once you master it, you can read the story that every electronic device is telling, from your phone to the entire power grid. So the only real question left is, what stories are you going to choose to read?